look inside.
Magic in your eyes.
Yeah.
Hi. In continuing with the lessons about operational amplifiers, and especially about comparators and gain with inverting and non-inverting amplifiers, today we're going to have a bit of a look at a circuit which uses two UA741 op amps and see how they can be used together with a device called an LDR, a light-dependent resistor. The light-dependent resistor is going to be wired into a comparator, and the comparator will switch its output depending on the position or the how much ambient light is falling onto the LDR. And of course, when the output of the comparator switches, we can use that through a BJT to give us a bit more current to drive the coil of an electromechanical switch called a relay. And then the relay has contacts, in this case contacts which are normally open, but then if this BJT gets a high amount of base current and switches on, then we'll get current going through the relay coil, which will close those contacts together and bring in this 470 ohm resistor to the first 741 op amp. All right, let's have a look at the first 741 op amp. It's wired as a non-inverting amplifier and has a 1.8k resistor going to ground from the negative terminal, 22k ohm resistor acting as the feedback resistor. The gain for the non-inverting amplifier is given by AV equals 1 plus RF over Rin. So in this case, it'll be 22k. Oh, they're always hard to get those tops off. 22k be 1 plus 22k divided by 1k 8. And if we run the maths on that, I've done that, where did I put it? Over here. I got a gain of 13.2 times. 13.2 times. Now that's going to be case 1, because think about what's happening here. When this relay is energized, we're no longer going to have a 1.8k resistor there. We're going to have 470 ohms in parallel with the 1.8k resistor, because this 470 ohms is going to be going to ground, connected to the top end of the 1.8k, which goes to ground. They simply become in parallel. So we get a new gain equation. Case 2 will be 1 plus 22k divided by 1k 8, not plus the 470, but in parallel with 470 ohms. And that's going to equal a gain of a lot higher than we had before, 60. So the gain, it's a figure of merit for the amplifier. These are multiples. So whatever input voltage we're putting at the front of the amplifier, it'll be multiplied in case 1 by 13.2 times. Case 2 multiplied by 60 times when this relay is energized. What do we need to do to get the relay energized though? We have to have a bit of a think about this circuit. I don't need those notes anymore. Oh, look at this. This is nice. That's an operational amplifier template which I use when I do work on the board. I think I must be the worst triangle drawer. So I made that little template up, and it makes it very easy to draw operational amplifiers on whiteboards. I'll put that out of the way. Let's explore what's happening here with this second 741 operational amplifier. It's wired up as a comparator, and all comparators have to have a threshold voltage which they use as a reference to put a sample against. The threshold voltage here is connected to the positive terminal. 10k resistor, 12 volt rail. We're going to have the rail divided by 2 voltage at that point there. That's going to be equal to 6 volts. And the other terminal to the operational amplifier is connected to a 10k variable resistor, which we'll take a closer look at why that's in circuit in a moment, a 1k resistor. When you put a 10k resistor like that in the leg of an operational amplifier, it's quite common practice to put a series resistor with it called a limit resistor. So even when that 10k variable resistor becomes short circuit, if we wind it right to one end, we still have at least 1k at all times in the circuit. And that's a really essential thing to do with a lot of circuits. The light dependent resistor. Now this little critter, these have a range of resistances depending on the light value falling on the device. And I used a DMM to measure that, and I found that with my LDR I had 5.7k with the ambient light in the classroom, which is quite bright, it's full of LED lights, and 35k ohms when it's dark. Now, if I was to take that outside into a much higher lux environment with the sunlight, I dare say that ambient light value could even fall down below 1k ohm. I didn't try that. So knowing that then, the value on the LDR, the resistance changes depending whether we shield it from light. We're going to get, when it's shielded, we're going to get about 35k. And when we take that shield away and we get the light falling on it, ambient light in the classroom, we've got about 5.7k across that LDR. When I've got 5.7k across it, low resistance there, high resistance there. If I had 10k and 1k be 11k, 5.7k, I'm going to get a voltage divider set up there, and I'll actually get a higher voltage on this pin than what I've got on this pin. Let's review quickly what happens with a comparator. With the comparator, if I've got a higher voltage on the positive terminal compared to the negative terminal, the output of the comparator will swing positive. Alright, so let's have a think then about what happens if the output of the comparator goes high. We're going to get a positive current going into our transistor, which turns the transistor on. Transistor turns on, activates the current or puts current through the coil of the relay. Relay is energized, contacts close together, give us higher gain. If the output of the op amp swings low, then the transistor will be turned off. No current will flow down through the emitter, so the relay will be turned off, contacts stay open, and we end up with 13.2 times gain instead of 60 times gain coming out of our amplifier. I've done some calculations with the voltage divider with the LDR and its other resistors. I'll swing the board across and we'll have a bit of a look at that. LDR, or the terminal voltage at the negative terminal of the op amp, is going to be based on R3 plus R7 divided by R3 plus R7 plus R4. It's simple equation. It's always R2 divided by R1 plus R2 times the supplied voltage when you're working out voltage divider like this. It just so happens though that I end up with the R2 situation being made up of R7 and R3. So case 1, I've said when we've got bright light falling on the LDR, and I've set R7, which is the variable resistor, to 0 ohms. I'm simply going to have 1 divided by 6.7. It's 1k divided by 6.7k, but it's only a ratio, so you don't need to put those in the equation. Times 12 volts, 1.79 volts. Again, if R7, I make 0 ohms. By turning it, it's an adjustable resistor. When it's dark, 1k divided by 36k times 12 volts, only 333 millivolts. Those two values are going to be of no use to us whatsoever because we've got a threshold voltage here of 6 volts. And so these two values are going to be absolutely useless to us because we need this terminal voltage here to get higher than the threshold voltage, and neither of those go higher than 6 volts. So using the variable resistor down at 0 ohms just is not going to work for us. Case 2 then, I've set the variable resistor to its maximum resistance of 10k. I've run the maths on it. 11k over 16.7 times 12, 7.9 volts. Hey, that's exactly what we need. That's going to cause the comparator to change state. It's bigger than the threshold voltage. So it's going to cause the comparator to switch in the opposite direction. So neither of those values are going to be any good at all to us because they are both less than the threshold voltage of 6 volts, and we need to get something larger than 6 volts at this terminal here to be able to switch the output of the comparator in the opposite direction. So I've done a case 2, and I've considered this time putting the variable resistor at the other extreme, which is 10k ohms. I've looked at the two conditions, bright light and darkness, and in the first instance with the 10k at maximum, 11 divided by 16.7 times 12, hey, 7.9 volts, exactly what we need. Now, if that's the situation, bright light, that terminal is going to be higher than that terminal. The output of the op amp is going to be driven negative. When the LDR becomes dark, with the 10k resistor at maximum, 11 on 46 times 12, 2.87 volts, absolutely magic. We're going to be lower than the threshold. Positive dominates, the output of the comparator is going to go high. So this is what I've done. This is why I've put the 10k resistor in that leg. It was like an experiment to see where I'm going with this particular LDR. Now that I know that 10k, 8k perhaps, somewhere up that top end is going to work beautifully with the mathematics and cause the switch to take place. So the other things that I had on this board, they are the different value resistors. The R3, 1k, R7, R4, they are all labelled down on the circuit down here. The LDR again, 5.7k ambient, 35k when it was dark. Alright, let's go back to our circuit again. And let's just check our recording again, and we are still recording. There's definitely something wrong. Got a bit of problem today with the video card in the camera. I did notice that the first couple of times I turned the camera on, it was giving me a write protect error, and then the camera stopped recording a couple of times. So I think probably that SD card might be retired to the garbage bin. Can't afford to have a video recording where the recording stops abruptly partway through the recording. So far so good with this SD card. We haven't had the same malfunction. So I'll make sure I label that other SD card. Alright, so it's time to go now, I think, and have a look at the experiment, the way it's been set up, the lab, and we'll see that when we change the brightness level on our LDR, that we in fact do change the gain through the first operational amplifier. Lovely circuit, gain controlled operational amplifier done with an LDR for lightness and brightness, for brightness and darkness, so that the gain would be different in daytime to what it would be at night time. You can probably think of a stack of different applications where this particular type of circuit would be used. And you might also consider that you could probably come up with some other type of switching for this, but got to be a bit careful because you need to actually take that down to ground to put it across that. There's probably other ways that you could do this. You could probably use a solid state relay there as well. And if you did that, you could probably eliminate the current driving transistor that I've used in this circuit. But I had that relay at hand, and we used it. So let's go now and have a look at the actual lab setup on the bench and see if it works to the same gain values that I worked out with the maths on the board. This is how I've got the lab set up on the bench. I've got the parts breadboarded on an SK10 board, and then I've got a split rail power supply. In fact, I found out that this relay, the coil was a little bit stubborn to pull in. It's a 24 volt coil, and although the holding current in these is quite low, you need a bit of oomph to get them to go. So I had to up my voltage on the op amps to 15 volts, positive 15 volts, negative 15 volts, to get enough drive current to pull in the relay. I've got the oscilloscope set up here. The yellow is the 100 millivolts peak to peak input at 1 kilohertz, and the blue is showing me about 1.4 volts peak to peak. Well, that's a gain of 14 times in ambient light, and that's a little bit higher than what the math said. The math said 13.2, and I've got there 14. I'm not too worried about that. It's pretty close. I'll cover the LDR, and you can hear that relay changing state there. Cover the LDR, and now I've got a voltage peak to peak on the output of 6 volts divided by 100 millivolts coming in. That's a gain of 60 times, and that's what we said. In darkness, this thing should have a gain of 60 times. So math said 13.2 ambient, we got 14. Math said 60 in dark, we got 60. We haven't done too bad. I think on the day that's pretty good outcome. I'll bring the camera a little bit closer to have a close-up look at the board. Let's just swing the camera up here. There's the Rigol oscilloscope and the signal generator running next to it. So here's the lab board. That's that relay. It's a nice little Omron relay. Like I said, it is 24 volts coil voltage, 24 volts DC. So it was the only relay that I could find. I did have a 12 volt relay somewhere, but 24 volt relays are quite common because they're used in industry all the time, unlike 12 volt relays. Here's my LDR. Don't know if you can see it on the screen, but it has a nice little wiggly line on the front. And there's my 10k ohm resistor. This is my comparator operating in the first part of the circuit. And this diode is the protection diode across the coil to prevent back EMF damaging the output transistor. And behind the relay, you can't quite see it there, but there's a small BC109 transistor. This operational amplifier here is actually the first one on the board, and that's the one that has the gain of 13.2 and 60 depending on the input resistance, which gets switched with the relay by the comparator. I'll move that camera around just a little bit. There you can see now the BC109 that I've used. Use these for just about everything. Really versatile transistor to use. NPN can take about, I don't know, 50, 60 milliamps I think through them before they start to go into meltdown. They're pretty versatile. I always keep those on hand. And there we've got our darkness and lightness. So that's it. That's the lab and the circuit explanation for the operational amplifier used as an amplifier in the non-inverting configuration, and also an op-amp used for a comparator connected to an LDR. I hope you found that useful, and I think this is video number 97. So we're nearly at video 100. We're doing all right. This is Greg Moore for New South Wales TAFE. Thank you.
Magic in your eyes.
Well, I think it's fair to say that video had its fair share of editing problems. One little mistake on the board with the plus and the minus in the wrong place. Oh dear, so much time to fix. Don't want to do that again.